Good afternoon. Welcome to Psychiatry Grand Rounds. This is Child Psychiatry Grand Rounds today, and we have switched the date this month. And we thank very much our speaker for coming and joining us today. Dr. Luan Gherkin is a professor of psychology, linguistics, and cognitive science with an adjunct appointment in speech, language, and hearing sciences at the University of Arizona. Dr. Gherkin received her PhD from Columbia University and received tenure at the State University of New York at Buffalo before joining the University of Arizona faculty in 1995. Dr. Gherkin has served on NIH and NSF grant review panels and has been continuously funded by those agencies since 1992. That's very impressive. Those of us that live in the races for funding know how valuable it is to have been continuously funded. Congratulations for that. She's currently associate editor and co-founder of the journal Language, Learning, and Development. Throughout her career, Dr. Gherkin has used a range of techniques to study language development in infants and children, and has directed her research at addressing both practical issues and classic questions about the nature of human language and its relation to the human mind. In addition to her work on language development, Dr. Gherkin is involved in efforts to restructure academic institutions to promote broader participation and greater equity. So please help me welcome Dr. Luan Gherkin.
Well, thank you for coming. All right, so I'm going to tell you about some research, both from my lab and some other labs that's relatively new. And the research focuses on three types of findings. So the first finding is that we get dumber as we get older, basically. That we start out with a very broad range of perceptual abilities, which we lose, and we lose these in a whole variety of domains. But that makes us more efficient in our particular environment. So we're efficient as adults, but dumber. The second kind of finding that I want to talk to you about is that infants are surprisingly good at learning from a very few examples, and in fact they learn better from fewer examples than from more examples. And third, there's a connection between motivation or emotion and learning, such that infants are motivated to attend to those aspects of their environment that seem to have some kind of underlying pattern. And so we can talk about those parts of the environment that seem to have some kind of explanation. Okay, so here we go. Starting with the first one, I'm going to give you three examples of learning and loss. And so, as I was saying, as we get older, we get dumber. So by the time you get to poor Bart's age, you're just not very good at all. And so three examples, two from our lab and another one, all of which show that younger babies can perceive distinctions that older babies can't perceive. And in all of these studies, the approach that we're going to be taking is that we'll test two or more age groups, show a difference in what they can learn or what they know when they come into the lab, and then try to see what it is that's going on in their environment that could have caused the change. So what is it about their environment that they're extracting so that they would be changing over time? And we'll show that the parts of their environment that probabilistically or statistically just isn't very good information, that's the part that they get rid of or they lose. So I'm going to start out with an example not from my lab but from another lab, and that is the loss of ability in face recognition. So it turns out that adults who have lots more experience with people of one race than another race are poorer at recognizing faces of people of the other race. And this is often referred to as the other race effect. Now, why do I have a picture of a wolf up here? The reason is that if you were raised by wolves, as I was, then you might find yourself, as a young person, actually being able to tell the difference between lots of different wolf faces, but not so good at telling the difference between human faces. And so the point that I want to make here from the get-go, because I think it's important for thinking about the infant experiments, is just that what we have experienced, it doesn't depend on our species or race or anything. It actually depends on what we're exposed to in our environment. So having said that, we can ask, well, okay, when does this kind of effect start? And you might guess, well, maybe in school, et cetera, et cetera. It turns out that it probably starts much earlier than that. And so to look at the other race effect in infants, the way that these researchers approached the problem was a two-stage kind of experiment. So there was a habituation phase, so babies get to look at a picture of a person for as long as they're interested. And then they're tested they get to see that same face again, but in some other orientation, and a different face. And the question is, which face are they most interested in? And there are two groups of babies in this experiment. So for some of the babies, the babies will see either pictures of their same race, but basically people that they've seen frequently, versus people of a race that they haven't had much exposure to. And the babies are 3-month-olds and 9-month-olds. So the way the experiment works, so we could do this with you as an adult, except for we couldn't wait till you got bored. We would say, okay, the guy on the left, he's Bob. So which of the two guys on the right is also a picture of Bob? So the way we do it with babies, though, is we show them the face on the left until they lose interest, which takes on the matter of seconds. And then we show them sequentially the two faces on the right, and we see which one they're most interested in. So if the babies are Chinese babies, then they show most interest in the top face because that's different than the one that they'd been exposed to, the one that they'd gotten bored with. And they do that at 3 months and at 9 months. So they maintain their ability to tell the difference between the faces. But now let's look at the same Chinese babies. And now they've got a face that they're a Middle Eastern face they're not used to looking at. So again, they see the face on the left. That's Susan. Which of the two women on the right is Susan? So they look at the face on the left until they lose interest. And now they see sequentially the faces on the right. And it turns out that only 3-month-olds can discriminate the faces. By 9 months, they can't do it anymore. So what's going on there? Well, it seems like it has something to do with the statistics of facial configuration. So for people of different races, there are different cues that are the best cues for recognizing the difference between individuals. So proportion of forehead to the rest of the face, eye spacing, nose to mouth spacing, etc. And it turns out that if you actually train a machine, a computer, to recognize faces, it will quickly show you the other race effect. So there are statistics in the environment, and either babies or machines can pick up on these statistics and quickly home in on that kind of information that is the most helpful for being an efficient face recognizer. Now you might think, might ask this question, well, what happens with babies who are exposed to one set of faces early in their lives and then another set of faces later? Well, it looks like we're somewhat flexible in this. So there have been a number of adoption studies, primarily of Korean infants who at age 2 or 3 were adopted by French families, and it appears that they go through a period where they also show the other race effect for French faces, but quickly are able to adapt and become skilled or tuned up in that other configuration of faces. Okay, so we can talk about the same kind of effect in a number of different domains, but the other two experiments that I want to tell you about are not based on experiences that the baby comes into the lab with, but something that we want to teach the baby in the lab. And so I want to show you how we do that. So we bring babies into a sound attenuated room, and they usually sit on their parents' lap. We expose them for a couple of minutes to some novel input that they've never heard before. And then we test them on alternate trials on patterns that either fit or do not fit that input. And we're just, again, very similar to the logic of the last study that I showed you. We're looking to see which thing they show more interest in. So this is what it looks like. And you'll get to hear a happy baby. This isn't an actor.
Cody. Popody. Popody. Cody. Cody. Popody. Cody.
Okay, they're done with that trial. Now they're moving on to another one.
Codico. Podipo. Podipo. Code.
Ooh. That was strange. Okay. So that's what the procedure looks like. So we expose babies for some period of time in the lab, and then we test them in their orientation toward a particular speaker. So we can talk about that kind of experiment in two different domains. So the first one we can talk about is in the domain of music, and this research is in collaboration with my former graduate student Colin Reimer Dawson. He just finished a PhD in psychology last year, but because you can't ever get enough PhDs, you should collect a set. He's now doing another one in statistics with an emphasis on machine learning. So he familiarized babies with 2 minutes of a musical stimulus that sounds like this. So I won't make you listen for the full 2 minutes, but they listened to 2 minutes of something like that. And then on alternate trials, they got this kind of test stimulus. So same or different? Good, good. Okay. So that one was the same. And so this is a really interesting effect. So it turns out that the same time we were doing this, somebody else was doing it with rats. And rats can show evidence of having learned this. So as you noticed in your little sample, the first note repeated. And rats seem to be able to do that. And 4-month-olds seem to be able to do that. But by the time infants are 7 months old, they can't perform in this task anymore. They can't tell the difference between the good examples and the bad examples. So again, we can say, why is that? What causes them to lose their ability? And it seems to have something to do with the statistics of their musical experience. So in particular, the structure of Western tonal music, and that's all the music that babies are going to get to listen to. So when they're listening to baby-directed music like Mary Had a Little Lamb, or when their parents are rocking out in the car, it's all going to be the same, that the music that they're listening to has keys and octaves with 8 notes per octave in each key. And so the question is, when do babies figure out that structure? Well, we know that 4-month-olds haven't figured out that structure, because if you play a 4-month-old a tune in a particular key and then play them that same tune transposed into another key, they won't recognize it. They don't have any sense that it's the same tune. Whereas by 7 to 8 months, infants can recognize transposed melodies. So they can recognize Mary Had a Little Lamb in the key of C or in the key of A, etc. And so what that means, once you have some ability to perceive the structure of music, what you actually are perceiving, or what you're picking up on, are statistics that look like these pink bars here. So what I've got is so I've just played you a note. I've just played you middle C in the key of C. And so what I've got here is the likelihood that the next note is either another C, that's the middle, a B, a D, an A, an E. And just because of the nature of music, we tend to have a smooth probability distribution. So the most likely note after I've played you a C is another C. But then the second most likely notes are going to be D and B, etc. And so what you see here is that there's a lot of repetition in Western tonal music. And so that causes, by the time the infants are 7 and 8 months old, they say, oh, well, that's just how music works. So paying attention to repetition per se isn't interesting anymore. It doesn't have any special status because they're used to that kind of structure. So we think that that's why they lose their ability in this experiment to do something that even rats could do. I think the hallmark case of loss in development is in language. So we know it's much, 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 much harder to learn a second language as we get older. We lose the ability to perceive pairs of sounds in a language that we don't use. So for example, here's another little test for you. Are these sounds the same or different?
Dal, dal.
And then?
Dal, dal.
That was hard, right? So the first pair, they were different, and the second pair weren't. And that's a Hindi contrast that you make by putting your, if you say dal and you curl your tongue back, that's called a retroflex sound. And the other one is duh, where you put your tongue behind your teeth. That's a very hard sound, especially in running conversation, for non-Hindi speakers to perceive. So we can ask, well, okay, what happens with babies who are either exposed or not exposed to that language? So this is fairly old research at this point, but it follows the pattern that you've seen already, that 6 to 8 month olds who are learning English, not Hindi, can perceive that kind of difference that I just played you. But by 10 to 12 months, they can't perceive it any longer. So they've lost their ability to perceive that contrast. But luckily, as you might expect, 10 to 12 month olds who are learning Hindi can perceive the contrast. So we're seeing another example of babies getting worse on perceiving differences that they're not exposed to or that aren't statistically important in their environment. So we can ask a slightly more sophisticated question, not just about, well, when do they lose things, but how does it all work? And one possibility is that, at least in the domain of language, there's some kind of a little menu or checklist of possible distinctions that a language might make. And you just kind of wait and listen in yours and say, yep, mine makes that distinction. Yep, mine makes that distinction. The other possibility is that babies are born with a much broader range of abilities and sensitivities than are ever really used in a particular language. And these are narrowed via experience, but it's not like a checklist. It's more like a kind of free range, just trying to decide what's important. So to look at that, we did another kind of study using the method that you saw with the video. And in this study, we were interested in how infants thought about the stress patterns in multisyllabic words, so which syllables get most emphasis. So they were familiarized with stimuli like these. Tita mifa, mifa salata, bom bom latida, lata bom, fasa latida. So they would hear something like that for 2 minutes, and then they got these kind of test items.
The tone remifa, the tone mafasa, the tone fasola, the tone,
or these.
The re tonfa, remifa tonsa, mafasa.
Any guess there about which one was matched the first thing you heard? Adults don't do very well in this experiment. So it turns out that babies, 9-month-olds, can do that experiment. They perform very well in that experiment. So we can contrast two different kinds of rules or information about language that they might learn. So one was like what you just heard. So a rule says, the rule about stress says that you should put stress, emphasis, on syllables that end in a consonant, and those are sometimes called by linguists heavy syllables. So in this particular experiment, you heard a bunch of words that had these syllables that ended in a consonant, there were 3 different syllables, bohm, kier, and shul, and then the test words had a different heavy syllable tone. And 9-month-olds do fine under those conditions. We can contrast that with another rule, I didn't give you this example, that says stress syllables starting with T. Now, so the familiarization words you stressed all the syllables that were tu, ta, and ti, and then the test words started with T also, tone, just like the other language. And so the question is, this is a rule that doesn't ever occur in any language. It's outside of the range of human language. Is it something that we can learn? Well, it turns out that if we focus on those, the rule that doesn't occur in any language, 7-month-olds can learn it, but 9-month-olds can't. So here's another situation where we start out with greater sensitivity and then we lose it. In the example that I gave you, where you look somewhat puzzled, 9-month-olds can learn that, but adults can't. So it's okay that you didn't learn it. So again, we have another example where babies are getting worse over time, and that they're getting worse for different kinds of information at different times. So finally, again, we can ask why are they doing that? And there are probably 2 reasons why we're seeing the loss that we see. One of those is with respect to the weird rule that no language has, that you should stress all syllables starting in T. The frequency, there are lots of syllables in English that babies are exposed to that start with T, so stressed syllables starting with T are frequent, but if you actually look at the likelihood that a syllable gets stressed if it starts in T, that's no more likely than chance. So basically the statistics of the input that the babies are getting say if they're paying careful attention, you should really not notice the beginning of syllables. It doesn't have any bearing on whether they get stressed. But that kind of thing might take babies a while to do, so at 7 months they don't know that, but by 9 months they do. Now the difference between 9-month-olds and adults, the loss of the ability to say, okay, you should stress syllables that end in a consonant, it turns out that there is actually some statistical evidence for this in English. So syllables ending in a consonant do tend to be stressed in English. But it's also the case that in English, if you think about it, if you think about words that you know, most of them start with a stressed syllable. So we have lots of words like apple, mommy, doggy, and not that many words like giraffe or banana. And so the statistics of English say, well, we like to have stress on the first syllable. And so it makes us a lot better, a lot faster at finding words in English if we just look for the stress on the first syllable and not pay attention to other nuances. So the 9-month-olds are still paying attention to all of this other information, but by the time we're adults, we're just not very tuned into that other information anymore because we have a way of being very efficient by just paying attention to the beginning of the word. So to summarize this section, learning and loss, we're born with a very broad range of perceptual abilities, it appears, and in fact, we're probably born with a broader range of perceptual abilities in language, in music, in face perception, in all kinds of domains that we never actually even need to draw on, even if we're as adults. So we have this this is very odd. We have this system as infants that we need to narrow. So becoming maximally efficient, becoming very fast and efficient users of language, of perceivers of music, of perceivers of faces, entails that we need to downweight a lot of perceptual distinctions that we could make when we were newborns. And the timing of the losses depend on the amount of evidence there is. So it's not like the state of your brain at age 6 months just says, okay, ignore all the information that you haven't had to use so far. But rather, we seem to be, our abilities seem to be changing in step with how much information we get in that particular domain in the environment. So there's this interplay between the perceptual losses, which are clearly being driven by some changes in the brain, but those perceptual losses are happening on a case-by-case basis with the amount of information that we're getting. It's not happening kind of across the brain altogether. Okay, let's move on to the next example, and that is that infants learn better from fewer examples than from many examples. And so that is just that if you show them a few examples, like 3 dogs, and you say these are all dogs, that's kind of an optimal number of examples. So we can talk about that as 3 seems to be a really important number of examples. And we can see this in lots of folk culture as adults as well. So a man walked into the bar, there's always 3 things that happen. We talk about things in terms of 3s quite a bit. And it turns out that 3 is also very important for learning in infants. So this is another experiment that uses a very similar methodology to what I told you about before, but now it's visual. And so we have one group of 3 to 4-month-olds. This is not from our lab again, but a lab that does related research. One group of 3 to 4-month-olds, and they experience 6 trials like this. So they get to see each of those trials for as long as they're interested, and then they get a test, and we're interested in seeing which test item they prefer. And so what you saw before were things arranged in vertical columns, so you might think that at tests they would look longer at the horizontal because it's new, but they don't care. So babies in this experiment don't show any preference for the vertical versus the horizontal. Now contrast that with another group of 3 to 4-month-olds, and they get 6 trials like this. So there were 3 different examples, each repeated twice. Now they get a test, same as before, but they show the preference for the new thing. So it seems like having been exposed to just 3 different examples in random order allows them to pull out a pattern that they couldn't perceive when they were just exposed to the same pattern just once. So it seems like getting a little bit of variety but not too much is really optimal for babies to learn. Now we can see a very, very similar kind of thing in the language domain. And so in that stress syllables experiment that I just told you about, what we see is that infants the 7-month-olds only learn the stress syllables starting in a T if they get 3 examples. They don't learn it if they only get 1 example. And the 9-month-olds only learn the rule stress syllables that end in a consonant if they get 3 examples, but not if they get 1 example. So we're seeing this is coming up in experiments in lots of different labs that 3 seems to be a really important number for infants to generalize from, to learn patterns from. So we can ask then, all right, they're really good at learning with 3 different examples, but do they actually learn better from 3 examples, or is it just that they have this ability but they would do better with more? So an experiment that we've just finished, or we're waiting for one more 11-month-old to come into the lab, but we've looked at this in our lab, and so we created this set of words. And the words all are of the form consonant, vowel, so pota, posa, tofa, baza, etc. So some of the babies in the experiment get just 4 examples. So they get the things in yellow: pota, tapa, biza, deva. And they hear each of those words 6 times, just because we want them to be able to remember. But they only get 4 different words. Other babies get 24 different words. So they get the 4 yellow words plus all the white words, and they hear each of those one time. And then at test, they get brand new consonant, vowel words, the ones in turquoise. And the generalization or the rule that we see in these words is that the first consonant and the last consonant have to have the same voicing. Now, this is a linguistic distinction, and you can do this in the privacy of your own home, but if you go t, 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 your vocal cords don't vibrate, and p, 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 your vocal cords don't vibrate, but if you go b, 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 your vocal cords vibrate, and z, 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 your vocal cords vibrate. So when your vocal cords are vibrating for both consonants, that's a match. So that's the nature of the rule. So we first of all tested, this is the strangest thing that's going on here. We first of all tested 9-month-olds, thinking they would be good at this. And it turned out that 9-month-old girls could do it. So they learned better if they got 4 examples 6 times than 24 different examples. But we just stopped the experiment because it was only the girls who were learning. Another thing that we keep finding, that girls are faster. What can I say? So then we moved to 11-month-olds, thinking, okay, well, everybody would be on board by then. And so we were just finishing this up. I actually put N as 36 because I thought for sure we'd get that last 11-month-old by now, but we're still waiting for that child to come in. So anyway, what we find is that the babies who are exposed to 4 different words 6 times each do learn, but the babies who get 24 different words once don't learn. So what this tells us is that it's not just that a handful, 3 or 4 examples, is helpful for learning, but it's actually optimal. That a small number of examples that illustrate a particular point for a baby that allow them to learn a pattern is the best number for them. And again, we can ask, what about adults? The adults actually have a hard time learning one of the rules that we gave them at all, which you shouldn't be surprised at this point. But interestingly, adults don't seem to learn any better from the fewer or the more examples, so they learn equally well. What we did find is that adults are more confident, so they're more likely to say, yep, that's an example, yep, that's an example, if they've heard 24 different words during familiarization than 4, but they're wrong a lot of the time. So they have a yes bias, but they're equally able, in both cases, they're significantly above chance performance, but they're equal if they got 24 examples or 4. So this is another really interesting puzzle. Why are adults different than infants? They're not only not quite as good at learning, but they seem to learn under different conditions. So quick summary of that section. We can see that infants and children are able to learn quickly from a very small number of examples. 3 seems to be perfect. They also learn better from a fewer number of examples than more examples. Doesn't seem to be the case for adults. We need to investigate this more, but it seems like it's not the same for adults. And then one of the things that we're going to be looking at as soon as that 11-month-old finishes up with us is whether it's the number of repetitions or the number of examples. So we're trying to look at the interplay of memory and learning. Okay, so I can move on now to the last section, and I want to talk about how infants appear to be motivated to learn or to explain. And I'm very interested in this line of research, and I think that of all of the things that I'm going to tell you about today, I think that this one has the most potential for some interesting collaboration between your side of Speedway and our side of Speedway. So all the studies I've told you about so far are ones where we look at babies' preference. So do they like new things or old things? But, you know, we're bringing them into the lab and we're playing them these weird kind of stimuli. But for some reason, they seem to sit through it and learn, and they give us some results. And so we started to wonder, well, what's the motivation? I mean, they're not getting anything. We're not giving them Cheerios or toys or anything. They're doing it. And so it turns out that people have been thinking about this problem of motivation in learning for a long time. So this is what Thomas Hobbes had to say about it. He said that there is a lust of the mind by a perseverance of delight in the continual and indefatigable generation of knowledge. So that's some good 17th century language. But he's basically arguing that we have a great drive toward understanding, toward explanation. Now, a more modern thinker has also talked about that. So in her article, I can't believe she got away with this in machine learning, but she had an article called Explanation as Orgasm. And so she said that the cognitive system is accompanied by a theory drive, a motivational system that impels us to interpret new evidence in terms of existing theories, etc. So both of these people are really painting us a picture of learning as a drive, of explanation as a drive. And there's been a lot of interest in the last few years about thinking about infants and young children as engaged in science, as approaching their world as scientists. Of course, implicitly, they're not thinking, okay, I've got to test this, I've got to test that, but they're really actively engaged in trying to figure out what's going on. Now, in the interest of time, and hopefully that we'll have some time for some questions, well, I guess I can tell you about this really quickly. So this, again, is not my research, but it does show you how to think about learners as scientists. So again, this is going to be an experiment with two groups of kids. These are 4-year-olds. And in the experiment, there was a toy, a device, in which if you press down the white lever, the little guy pops up, and if you press down the black lever, the duck comes up. But children weren't shown how that worked. And so in these poor kids, they had to do everything with the experimenter. So the experimenter would press down one lever, the child would press down the other lever simultaneously, and so both things would come up. So that didn't provide any information, because you didn't know whether pressing the white one would make them both come up, or the black one would make them both come up, or if it was 1-to-1. So the child was deprived of knowing how this exactly worked. So the experimenter walks away and then says, okay, here's the original toy, here's another toy. You can just play with one of these and I'll be back in a little bit. And so children were being videotaped, and the question was, which toy did they pick? Now, when they didn't know which lever made which thing pop up, as in this condition, they would continue to play with this toy to figure it out. Now, kids in another condition, 4-year-olds in another condition, they pressed down the levers with the experimenter the first 2 times, but then the experimenter said, well, why don't you go ahead and you press one down, so they could see that pressing one lever made one animal come up. So same scenario, the experimenter then says, okay, I have to go and do some stuff over there. You can play with this toy or this new toy. Which one does the child choose? Now the child will choose a different toy, because they've already solved the puzzle back when they were doing the experiment with the experimenter. So this shows, and there's quite a lot of research at this point showing that 3- and 4-year-olds are very, very good at designing little experiments with toys to figure out how they work. So we've recently completed a study with even younger kids. These are 17-month-olds. And this is in the domain of language, since that's an area that I'm interested in. And in this experiment, we let children listen for as long as they wanted to 2 different kinds of language stimuli. So in one of the cases, there was an underlying structure. So Russian is a language that has masculine and feminine words like Spanish, Italian, etc., and different endings on words go along with the masculine and feminine gender of the nouns. So we gave them a little sample of Russian, and we already knew from another experiment that they could learn this pattern. So they got some feminine words, and they had 2 endings, and masculine words that had 2 endings. And so we let them listen for as long as they wanted. And we contrasted that with another language where we put all of the endings on all the words. So we put the feminine endings on the feminine words, but we also put masculine endings on the feminine words, et cetera, so that there was no underlying structure. It was just a list of words with a bunch of endings on it. There was nothing to figure out. And we let them listen for as long as they wanted. And it turns out that 17-month-olds listened a lot longer to the thing that had an underlying structure. So that's in both of these are 2 different versions of the experiment. The red bars are the ones in which they got the learnable or the explainable input. The black bars, or the black line, is the one where they got the unexplainable input. And I'm just showing you the first 8 trials. So the red bars, the red line goes out for many more trials. So on average, those babies would listen for 20 trials or more. They really were interested. Whereas the babies represented by the black line, they really did stop listening after a few more trials after 8. But every baby listened for 8. So I'm showing you where we can compare them. And one thing that you see is that the red line is just a lot spikier. So babies, they would be, so this is reflecting their listening time. So they'd listen for a while and they'd get bored. But if they had the explainable language, their listening time would pop back up, and then it would coast down, and then it would pop back up. And that happened all the way out until they just stopped listening altogether. So, so they kept showing renewed interest, or it was as though they were actually finding new things to listen for in the data. So we can summarize that section by saying just that there's a lot of evidence from a lot of different labs that babies are really approaching their input very actively. They're not just absorbing it. I think that these latter studies show an important relationship between affect and cognition. That is, that babies do seem to have some drive to pay attention to, or pay more attention to things that have an underlying structure. And we're trying to get at that more in our lab right now. I think this raises a really interesting question about developmental disorders. Are there developmental disorders that appear to be about cognition, but are really about the interplay between affect and cognition? I think there's a lot of things that we might think about there. So, okay, so to summarize the whole talk, often when I talk with parents and grandparents and my students in my classes about how amazing babies are, what great things they can learn, they always say, yeah, they're just like sponges. So if I don't do anything else today, I'd like to disabuse you of that idea that babies are not sponges. They're actually a lot more like scientists. They're taking a much more active approach to their environment. They're not just absorbing information, but they're actively organizing the information, setting aside information that doesn't seem to be relevant, spotlighting information that does seem to be important or relevant. So like scientists, they use the statistics of their environment to rule out or weigh downweigh some kinds of information that doesn't seem relevant. They need only a few examples to see a pattern, so they don't, the ideas that they get about what might organize their world come to them after they've only had a few examples. And they seek explanations. So all of these suggest that babies are really approaching their world much more actively than I think we had been thinking for the previous decades. So let me end there and thank all of these people. Sarah Knight, my lab manager, is here, and all of these other people have contributed to the research. And thank you very much, too, for coming, and I'm happy to take questions. Yes?
You have a quiet audience. I have an interest in sex differences.
Uh-huh.
So in terms of in terms of the observations that girls are learning quicker in some of the tasks. Can you say a little bit more of what underlies that?
Well, I mean, I think that there have been hypotheses out there about the prenatal environment and different hormones that babies are exposed to prenatally, and so boys tend to be exposed to more testosterone in utero, and it actually turns out that probably has differential effects in language areas of the brain, and so they kind of start out with a deficit. Sorry, and I think that we see. I think it's a difference that we see quite a bit in infants, but it's probably something that continues on into childhood, that girls do seem to have bigger vocabularies, that they're using more complicated syntax, et cetera, into the school years. And so, you know, and there's been a comparable claim about spatial abilities in boys, and so, you know, we're not testing that, so we don't know. But you know, my sense is that they are on slightly different trajectories. I mean, they're all learning language clearly within some limits, but there are probably advantages that girls have throughout. So yeah, the emotion question, I've just really gotten interested in this lately, but I don't really have all that much to say about it. I think that I've got a colleague in speech and hearing, Elena Plant, who does brain imaging, and so what we're going to do is well, she may be doing it already, but we're taking those two versions of Russian that one of which the babies preferred and the other which they dispreferred. And we're going to, first of all, try that with some adults in the magnet and just try to get some sense about brain activity for those. And then we're also going to actually look at a group of adults with Asperger's syndrome to see if there's something different between them and adults with normal abilities in terms of how they respond to the learnable and unlearnable input. So we're trying to think of different ways we might come to this relationship between affect and pattern finding or learning. So if anybody has any ideas, I'd love to hear it, because I'm just fascinated in this topic. Yes, please.
Okay, so with the Russian experiment, who were the speakers that recorded that? Who was, first of all?
A native Russian speaker.
Okay, so then if the Russian speaker is kind of butchering their own language, might they have a distaste for that?
So,
might there be an emotional affect?
Yeah. Yeah, that's a great point. So we actually did two versions of that experiment. So the one that I told you about, and that was one of the graphs that I showed you. The other version of the experiment, it was all grammatical Russian, but it turns out that Russian has multiple cues to gender. And for both infants and adults, if you don't get two different cues to gender on a subset of the words, then you can't learn the pattern. And so what we did that time was we gave them the learnable version of Russian, where there were two cues on some of the words, and we gave them a grammatical Russian words, but that only had one cue. So we came at it from two different directions, and we think we've covered all the bases on that. But that's your question is great, because I think that some of what we see in that experiment is just that when you're producing ungrammatical words, you don't sound normal. Your voice, your prosody doesn't sound normal. So we came at it from two directions. Hopefully we showed virtually identical effects in the two different situations. Other questions? Yes?
So if you lose some abilities, infants lose some abilities when they grow up, where do you draw the line when it is pathological? Because some of these abilities are amazing, right? So having them later in life would be extraordinary.
Yeah, and I think it's interesting. I've been teaching an undergraduate seminar on creativity this semester, and a lot of these issues have come up because what we tend to do as normal adults is in order to become more efficient, we actually partition our world quite tightly into domains and so we develop special processing skills for each domain. And it seems like one trait that we see in people who are thought to be highly creative is that they actually don't do that so much, so that they tend to make a smear across the domains, which makes them more creative, but also more childlike in some abilities. And so the world is not, they don't process the world as efficiently, which is perhaps why we see a lot of creative people self-medicating and withdrawing, et cetera. But probably, so I think that's one population that we can look at and say, well, they haven't really, I mean, obviously they've done it to some extent, but they haven't so tightly partitioned the domains of adult life. So, yeah. Other questions? Okay. Thank you very much.